I didn't think we were going to get another Oshkosh, but it looks like we can try. How many campers do we have here? That's what I thought. All the people that have a hotel room are still in it. My name is John McGinnis. I am the designer of the Synergy aircraft. I live in Kalispell, Montana. I have a little design business called MC Square Design. We do 3D solid modeling. I do a lot of the work in SolidWorks, but use a lot of other programs as well. My AIAA story started when I was about 12 or so, and I heard Fantastic Friday. Someone gave me a tape of that, so I quickly got an AIAA membership. That number's long gone, but it was the start of knowing that someday I'd build my own airplane. And I was inspired by a lot of people, most of whom we know very, very well. It almost went away though, because by the time I was in high school and was paying for my hours or whatever the Cessna 150 cost, I found out that I couldn't afford my taste in aviation. And if it wasn't for the fact that we as an organization reach out to a lot of people that we don't know about, I don't think that I'd be doing what I'm doing right now. You should never underestimate the impact and the reach of this type of work in this organization. Truly, it's amazing how much effect we can have on the rest of the world. So sometimes we'll get a little bit negative in our thinking. We'll be, lamenting the fact that we're not growing the pilot base or wondering what's going to happen with LSA and its young eagles have done. I'm the product of a 30-year germination. Okay, we never give up. I want to talk a little bit about Synergy. I know that some of you know very little about it. Others of you know a great deal about it. Most of what you can learn about Synergy is available online through either the Synergy Aircraft website and the links. But more of the stuff that we like to talk about is on Oshkosh 365. That's now archived. We'll be moving new content to the AIAA forums. And so I'll encourage all of you to look online. Just Google Synergy Aircraft if you want to find out more stuff. But before we talk about the details, and I will have a lot of time for questions and answers, I really want to talk about the bigger question. And that is why bother to do this? It's crazy. I told you I couldn't afford my airplane. I couldn't afford to buy an airplane. I didn't feel like I could even afford to put a few thousand hours into building something a composite kit like I wanted to. So what did I do instead? Come up with something new. I'm 50,000 hours into that. So it's not like I'm actually saving anything. But the reason why we have to do this sort of thing, it should be obvious to everyone. We have an extreme need to replace 330,000 aging general aviation airplanes. Everyone here knows we don't drive 1967 cars for the most part. We do revere them. We do take care of them. We do preserve them. But they don't offer the value proposition that the general public wants and needs. Our airplanes, we love them, but they don't offer the value proposition that the general aviation public actually needs. We need to fix the broken hub and spoke transportation system, and in order to do that, we need to understand what the problem really is. I don't think that since this is really old information, and we're resurrecting it out of the archives of the 1910s, 1920s, 1930s, that we're as intimately familiar with it as we should be. We don't fly airplanes using effective fluid dynamic techniques. This is a study of the problem. Gabriele and von Karman studied it in 1950, literally. And what they discovered was that most vehicles travel from slow to fast, from light to heavy, on a scale where this is energy use and that's speed. And when they found out that fighters and airplanes and bombers did okay, and battleships and merchant ships did okay, railroad cars did okay, and so on, but between 70 and 450 miles per hour, we do not know how to fly. We pay a tremendous penalty for trying to fly with a heavier than air aircraft. When the same information is put into a form that we're more familiar with, used to seeing, this is full power L over D at gross weight versus speed in miles per hour. And here is AirVenture. Okay, you can wander around and you can see all those airplanes, and that's where we're at. But what's possible is actually not the yellow line, it's beyond the yellow line. The yellow line is where we can get with present-day technology. This, folks, is an indictment of a century of aeronautical teaching that's based on a premise that's a little bit flawed, not very flawed, but it's a system unto itself. And if you take a step outside that system, you move from a closed thermodynamic perspective that uses what we call dynamic pressure, 1/2 rho v squared, into the paradigm of open thermodynamics, taking the fact that we have an engine, we have a fuel source, let's use that to modify this problem of viscosity of the air that we fly through. So synergy is really all about flying using the principles of open thermodynamics. There's been a little bit of misunderstanding about what I mean when I talk about open thermodynamics. I'm really not talking about heat, cooling, drag, anything like that. I'm partially talking about using engine power to control the boundary layer, but there's a little bit more detail about that we'll talk about later. So up until now, when we try to approach the Gabrieli von Karman limit, we wind up with special purpose aircraft. As most of you know, I'm entered in the NASA Great Flight Challenge. We sure hope we can pull it off to be there up to this point. If the fact that they hadn't wound up having to delay the contest, we would not have qualified to be in the contest at this point in time. But you wind up with special purpose airplanes like the Festival Taurus G4 and Rutan's products that we showed there on the earlier screen. The reason is that normally in order to get low induced drag and manage viscosity, we wind up with long wingspans. And so this is where we start. When I started talking about these principles on beyond streamlining, I imagine that most people would come up with in their mind something like our baseline aircraft. You know, it's pretty cool looking. I think people like that plane. It's a big, roomy, 4 or 5 place motor glider, but it has a lot of limitations. Very efficient, but it's not very practical. So we can't really call things like this state-of-the-art, even though we continue to produce long wingspan, high aspect ratio, relatively speed-limited airplanes that are difficult to manufacture and inherently expensive. So the problem of where we are on the graph here versus getting more L over D takes us backwards. If you take a typical general aviation airplane and you say, well, let's focus on the induced drag problem, let's give a longer wingspan, we wind up slowing down in the quest for more L over D. You don't necessarily need more L over D. What we'd like to have is greater fundamental efficiency. So as we go faster, we get a lot less need for L over D. I think that's the point we talked about earlier there. This is a significant statement. A lot of our wings are very narrow chord, very short chord Reynolds number, and that means that they're flying slow as respects the air itself. If you increase wing area, if you increase chord, you can hit a sweet spot in the Reynolds number versus drag equation. So you wind up having a little bit more opportunity. And that's illustrated in this graph. As we go faster with a typical general aviation airplane, we lose our L over D. So why are we doing this? Why are we going for more L over D or more speed instead of going directly at the problem? You have to take aim at both things at the same time. Less induced drag is critically important, but so is managing small-scale viscosity, the boundary layer turbulence that sucks your airplane and sticks you in place. I'm going to plant this thought in your mind just briefly because we'll get to a neat illustration of it here shortly. You can't see the air, so you don't really realize just how sticky it is. it's sticking to your plane. You're dragging it along. If you flew through a cube that was colored a particular color, and you could see that air, you would just be dragging it along the sky. You'd just be painting a big old stripe across the sky. And of course, we do see this from time to time in our wake vortices. You know, the wake vortices get dragged on for miles and miles and miles. That's what drag actually is. Fluids don't have any drag. D'Alembert proved in 1752 that a perfect fluid has no drag whatsoever. You can fly through at any speed you want to, no drag. But if I introduce viscosity into this equation, if I make it sticky, then you have drag on the small scale, which is the drag of the skin of the airplane, and we have drag on the large scale, which is the wake vortices of the airplane. So in other words, to get to the Gabrieli von Karman limit, we have to go intensely after wake vortices and after skin friction, both at the same time, because it's like the air is ketchup. The air is like ketchup, it sticks to everything. And you throw ketchup on the table, and I take a spatula, and I try and get it off. What am I going to do? Are you following this? Ketchup on the table. Clean it up. Are you going to have anything but a mess? No, your experience tells you it's going to be a mess. That's what your experience tells you. Your experience is wrong. That's truthful about what we fly in airplanes do. Okay? The idea that we have to drag the atmosphere with us is an incorrect assumption, and we need to go after changing that. So here's how we're going to do it. And I'm not saying that synergy is the only way to do this. In fact, I hope it's the first of hundreds of ways to do this. My goal is to propagate this technology and all of its ingredients into as many forms of airplanes as we possibly can, as quickly as we can. But we need to use laminar flow. We have a lot of planes that do, and they use good drag reduction, natural laminar flow, but they do that on the wings. And that's good. But most of the drag comes from the fuselage. So let's go after natural laminar flow on the fuselage. Wake immersed propulsion is a great way to do that. When I say wake immersed propulsion, I'm not meaning a pusher-prop airplane. A pusher-prop airplane is not necessarily very efficient. We haven't delivered on the promise of having the prop in the back. And as I usually do at Oshkosh, I usually present on prop design, get into a big long-winded spiel about this, but I think if someone would like to plug this laptop in, maybe, who knows what's squeaking there?
Your transmitter. Turn on.
Thanks, Tom. I gotta tell you, my family is the whole reason that I get to do this stuff. They have heart and soul, sweat and blood, put every single thing that we have as collected into doing this work. My father and my son and my daughter piled into a truck and drove 36 hours to get here. And when they were driving down the interstate, our suspension rig for the quarter scale model over here, one of the hooks came loose and smashed the nose into the trailer. And their hearts are on the floor. They're thinking it's all dead. They're trying to go to the hardware store, get stuff to patch it back together. They're sleeping in the tent by the airplane tonight. And, oh my goodness. It's just that kind of story, day in and day out, year after year. This presentation, by the way, is one I've used before. My daughter, Kelsey, is an aspiring graphic designer as well. She had a nice presentation already for me. I didn't have time to use it, so I owe my family more than I could ever express. Pressure thrust. Oh, I'm sorry, I got to get back to wake immersed propulsion. The kind of thing you need on the back of an airplane is a fan. It needs to have a lot of blades. It needs to have a small diameter. It needs to have a lot of pitch. That's a nutshell synopsis of what needs to be pushing our planes through the air. It's extremely efficient. But instead of having something like that behind a body that doesn't seem to care about the inflow field, we need to make sure that the body is a natural laminar flow body and that we put the fan behind significantly behind the point of transition, and that we use good inflow design so that we don't make that impeller fly in a terrible, terrible environment for making thrust. But wake immerse propulsion delivers the goods. It's at least a 20% improvement in efficiency over a standard tractor configuration if it's done correctly. The next point kind of conflicts with wake immerse propulsion, and that is that pressure thrust, as Goldschmidt evaluated, is a way that you cause the air that you've parted with your body to collapse back on the aft body powerfully, so as to restore the energy that was lost in expanding that volume of air and moving through it. Now, I don't know why, after 50 years, we still don't really understand or utilize this concept. It is not rocket science. It's pretty simple physics, but we don't have any proof, we don't have any flying concepts that are out there making this commercially viable thing so that we can pour the money and the dollars into it, refining and optimizing it. Pressure thrust is something we'll get into in greater detail here. Non-planar span efficiency, that's what Synergy shows. You know, we've got a different configuration here, just in case no one or someone doesn't understand the difference between Synergy and a box wing. Box wings are non-planar and they have low induced drag. Synergy is a double box tail. The upper flight surfaces are tails, and they are not lifting in normal flight, they are pushing down. So just to make sure you understand that this would be a possible flight condition. Okay? Very high angle of attack. That's the normal condition as we're pushing downward, acting by throwing air upwards, and I'll elaborate on that in a minute. Open thermodynamics is really the same thing as powered boundary layer control. It means using engine power and fuel and heat in ways that change the dynamics of our calculation system. When I talk about Synergy to folks that are heavily reliant upon the textbook mathematics, heavily reliant upon CFD and spreadsheets and other programs to deliver preliminary evaluation of an aircraft design, I have to tell them, look, you've got to get under the hood. Look at what your calculations are actually showing and telling you. Some of what they're telling you is only true 95% of the time. And when it's not true, it changes everything. So we're still in search of a better fluid dynamic calculation paradigm, a program that will do it right all the time and do it in real time. I've got a couple ideas about that, and hopefully we'll get to them. The last point is optimum volumetric displacement. That's subsonic area ruling. That means that we don't, we're not going supersonic here, but we're going to treat the design of the airplane as if we were. We're going to gently disturb the air, not disturb it with pulses, not disturb it with a huge variance in the cross-sectional area that we present to the plane, to the atmosphere. So the problem we have here is that these things are hard to combine, and science doesn't like me for combining them all at once, because how are we going to know what's really responsible for the results? You're supposed to change one thing at a time and have a nice control. And the only problem with that is it would take another 150 years, and we don't have it. We don't need complicated solutions and Rube Goldbergs. What we need is something that is sellable, that you want to fly, that works. It's got to combine all of these things together, and it's got to do them in a way that is economical, easy to use, and it delivers a solution for the general public. The general public is afraid to climb into your airplane, and they don't really like the experience when they do. Who wants to sit inside of a tin can with headphones on, bouncing around? What we really need is an airplane that can fly at high altitude, and get swiftly cross-country, directly point to point, and that will help fix the broken hub and spoke transportation system. Okay, so that's why we're doing this. It's been beyond our means, but it hasn't stopped us. We're going to keep right on going. The double boxtail configuration gives stability and control through induced drag reduction. And it uses a neat mechanism for that. Instead of being a box wing, like a lot of other airplanes that have been relatively unsuccessful are, it uses, again, a double box tail. And so whereas almost everything that has been populated out there in the design space about box wing designs has been commercially unsuccessful and or semi-dangerous, Synergy is inherently stable. In fact, that's one of the things that's most striking about it. It's solid as a rock. It also has some interesting attributes in its flight. When you turn, let me see if I can illustrate this. Looks like we're going to make a left turn here. Okay, that's a rather radical roll rate if you had that much deflection, which you don't. But let's say you had that much, a little bit of deflection less than what you see there. What happens is this is making a little more drag, and this is making a little less. And that's the opposite of what you'd have with a regular airplane. So instead of having an adverse yaw condition and the need to coordinate rudders when you turn, it has a proverse yaw condition, and it carves the sky. It just basically rolls and the horizon stays level, and you pull as many G's as you like. So the way that this manages wake vortex is we use large surfaces. You take little fingers or little winglets or little something or other and you put it on your wingtip. You can't expect to control large scale effects. There's a lot of energy that's thrown by your airplane at the ground. The air is thrown at the ground by your wing very effectively, very efficiently. And when you move 3,000 pounds of air toward the ground very rapidly, you're not going to control it with a little fingertip on the wing. So the way the winglets get more efficient is they get taller. And you can go as tall as you like. Just keep right on going. But there's a point at which structurally that doesn't make any sense anymore. So a winglet tends not to get very tall, and we learn quickly that it's not as good as increasing the wingspan. So instead of adding a lot of taller vertical surfaces to our airplanes, we say, oh, it's better just to increase the wingspan if we can get away with it. But Synergy says, okay, we're going to come up here and we're going to throw some air sideways with the winglet, and we're going to throw some air upwards with the elevon, and we're going to use that physics to reduce our induced drag. The air has already been disturbed anyway. We're not trying to violate any laws of physics. You don't get something for nothing, but when you have air that's already been thrown at the ground and you're acting against it, you get your stability and control for free. The zero trim drag component is possible using approaches like this. I don't know if we've got that or not, but we'll find out. Here's another way of seeing it. Physics of a wave and physics of wake vortex are quite different, but at least you can see that, right? The air is curling around and it's crashing down on our upper flight surfaces. And we're acting against it preemptively, throwing air the opposite direction. It makes for a strong, stiff, lightweight wing because we're pushing down on the wingtip instead of lifting up. Behind the wing at the tip are actually generating substantial downforce. Very high amount of it, as a matter of fact. And that's because we get to act against the wave vortex that comes off the tip of the airplane. So we're acting against it with the third aircraft, not just the winglet, but the upper surfaces as well. That's a little bit from an interview that was done at the Cafe Foundation at the Electric Aircraft Symposium this March. There's more to that, and it's available online if you Google it on YouTube or something. So let's talk about the ingredient technologies in a little more detail. Natural laminar flow gets you half the drag of a turbulent flow airplane. We're not doing it very much on fuselages, but we'd like to do more. We're doing it pretty well on wings, making a difference. But the next step beyond natural laminar flow is to use powered drag control. And the experiments of the past haven't been very promising because of the way that they were executed. Instead of having a massively complicated million-hole electron-drilled boundary layer control system, it's just not that complicated, folks. If you put holes in the back of your wings and drag enough air through it, you'll basically achieve what August Rask would achieve, which is huge increases in maximum lift coefficient and huge decreases in drag. So it's a mass flow problem. The experiments in the literature were all about, can we do this at supersonic speed on jet fighters? Can we do it at near transonic velocity on commercial airliners and so on? Its real application is most suited for the general aviation environment. So we've got an example of, we put together a little bit of a wing section so people can see how we're actually going to do that on the Synergy design. So we use small scale structures to manage viscosity on the small scale. And again, the air is sticking to your airplane. So we need to take that air that's stuck, drag it into the plane, and spit it back out. And it's simple to do that. Blowers is pretty efficient. For a 6 horsepower blower, you can achieve the same performance results as a 100 horsepower thrust increase. And that's open thermodynamics. So let's return to this illustration. The key to understanding how to fly with a heavier than air airplane is to manage the viscosity of the air. Ketchup is a familiar viscous medium. So you probably shouldn't be able to clean this up like this. But you can. This is called Swiddle. It's an industrial robot tool developed in Japan. And all it is a plate. The plate goes out, but the skin that's wrapped around the plate like a treadmill is fixed on one end and spring-loaded on the other. And the result is that the surface that's next to the object that you're touching doesn't move. It's a minimum centropy result. There you go, it disappeared. See, it is magic. Okay, so pressure thrust is how we do this with air. It's a little different physics, but the principle works the same way. You're trying to move through the air without disturbing any of it. Trying to not take any of it with you. And so in a pressure thrust concept like the old Oshkosh body here, natural laminar flow would be possible, except Oshkosh didn't do that. He tricked the flow clear up front, 10% chord. And so we have this, even a turbulent flow body can get back past the maximum thickness, and if you suck that boundary layer in and you spit it out the back, you know what kind of drag number you're going to have? How about 2% of what you would normally have for a body of that volume? This isn't me making it up, folks. You can read the studies yourself. And in fact, Boxtail's results improved by 20% over Soretta's results that were 20 years before him. And a recent University of Washington study, I don't know if it's been published or not, has gone another step beyond Boxtail. So in Synergy, the pressure thrust concept is minimized because we can't just do that when you've got a weight compeller. All we can do with Synergy is have a nice, gentle, concave transition, feeding the prop as gently as we can, and by this we recover the boundary layer drag. You won't get pressure thrust. In fact, I don't want pressure thrust. I just want zero drag. So that means good weight and Marx propulsion, and as I mentioned, the number of blades and their design really counts. I'm not going to show you Synergy's actual fan, but that's an idea. So what we feel like is necessary for the airplanes of the future to be commercially successful is to exploit the human factor needs and the aerodynamic needs together at the same time. We have to have big, roomy, comfortable airplanes that can fly fast, at higher altitudes, safely point to point. And we don't want to give up anything that we already know. Right? Why would we want to build a fast airplane? They just land too fast and kill people. Well, don't accept that. Build a fast airplane that lands nice and slow on a short grass field. Or do what we're talking about doing, which is going the next steps beyond synergy with designs that are even more optimized for their short field performance. A lot of people look at this plane and think it's two-place. There's a little ruse there. That's a 5 to 7 place plane, and it's huge. We've got a lot of room in it, and it turns out that we could be roomier yet if we wanted to. But I didn't count the number of square inches I would be sanding, folks. It's a big job. The quarter-scale aircraft that we brought here first flew in 2007. It was not designed to demonstrate any of the drag reduction technologies. Those were already demonstrated. What it was designed to do was to tell me whether or not I had my simulators lying to me. And it told me that they weren't lying at all. It told me that they were right on. Sounds pretty cool, but the drag sound that you hear is because we didn't have any of the gorgeous wing filleting on there at the time. It was done without any of the wing fillets at all, so there's a real turbulent flow environment into the prop. But that is about 2/3 throttle on a 2 kilowatt electric motor. The aircraft weighs 30 pounds, and it has it's not dynamically scaled at all. It's just proportionately scaled, dropped down from full-size version 18 Synergy. So it has about 16 times the drag of our full-scale airplane. The other reason that we built it, I'll go back to that slide here, was to validate the structural finite element analysis. I was concerned, there's no baseline for how this stuff runs and moves and bends, and I needed a baseline. So when we put this together, we found out that the stresses were quite manageable. The direction that they would occur in was totally different from what you'd expect, and we had to mitigate that with a lot of different things for the full-scale version of the plane. Is displacing the volume of air in the same way that a smoothly streamlined, optimized body of revolution will. And that has a lot to do with reducing the wing interference drag problem that everyone wants to point out exists with box wings. Box wing airplane in particular have a huge wing interference drag problem at each intersection. But when you have favorable biplane interference, you don't have that problem. We've got not only subsonic area ruling helping us out to mitigate the drag of intersections, but we also have this phenomenon of favorable biplane interference. And I want to mention just for a minute the fact that no program presently gets this right that I've seen, other than just direct element modeling and CFD. All your spreadsheet calculator programs and stuff like that, and the textbook methods, X-plane, they all give you negative biplane interference. And so if this was a wing pushing air down, and that's a wing pushing air down, you're going to have them fighting over the air in between. But what we have with Synergy is favorable or constructive biplane interference. Because they're operating at different opposing angles of attack, the upper surface talks to the bottom and the bottom talks to the top, and together they're able to accelerate and influence a larger volume of air than either airflow alone. It's a venturi. We're creating a venturi over each wing, and that causes favorable translations of the pressure gradients between the elevons, the winglets, the V-tails, and the wing, and your supposed interference drag problem pretty much goes out the window. What little remains is easily addressed by having a stagger and blended, really nicely blended configurations. We do have one of our actual winglets modeled up and then brought it. We'll have it at the Aero Innovate event later on. So that's mostly the overview of Synergy. I know there's a lot of questions out there, and I want to take them. If you have any more detailed information, want more detailed information, like I said, go to our website, our Facebook page, or Google Synergy Aircraft. And you'll find out a lot. And if you don't get your satisfaction there, give me a call or an email. Happy to answer your questions. Let's start down there. What do you got? Okay, the question is, the ultimate goal is it to create a kit from this aircraft. We've already learned that people want this plane, so we have to respond to a demand for it somehow. I designed Synergy to be a study in alternative manufacturing techniques and processes to deliver the kind of airplane improvement at the kit market level that we've seen in the radio control world. I used to build stick and tissue balsa models just like everybody else, and graduated on up with a monocoat, and I thought that was the greatest thing in the world. But nowadays, of course, you buy an almost ready to fly kit, and plug in 3 parts, and go fly your airplane. That's where the kit market can go if manufacturers are willing to shoulder the risk of their 51 or their 49%, which is how can we make it in 3 hours so that they can make it in 4. So there are ways that that process can be enabled, and Synergy has been designed as a modular system. We're almost done building the parts that we'll slap together in a week. And that's the idea, is that those parts are what the consumer will eventually get. The ways that you can do this are enabled by the design of the airplane itself. It's got a very large, strong wing, it's got a very large, roomy fuselage, so we don't have to scrimp on areas that would normally, like I've got my fuselage cores are up to 2 inches thick in places. And that just means that I can just print that part and fiberglass it. It's quick and it's easy.
How's the contest airplane coming?
How's the contest airplane coming? We are now going at the speed we should have been going about 18 months ago. The only difference is that now we have enough money to keep working on it. So we're making up for about a 9-month delay. And I would say that the odds are now 25% that we will make the Green Flag Challenge, which was never really our primary goal. It was just a nice $1.6 million bonus.
In your full scale, what's the square footage of your main
The square footage? The square footage of the Green Flag Challenge airplane or the K airplane?
The one that you're trying to enter.
Okay, the one we're doing right now is 156 square feet of wing and about 44 square feet of tail.
And that's going to be the equivalent of a 2-place?
The equivalent of a 2-place? No, it's a 6-place.
So you're going to be entering the competition for full?
Yeah, Synergy was designed as a practical electric airplane. The breakthrough was so significant that I couldn't put an electric motor in it. I needed to use something that was existing as a power plant. I selected the Delta Hawk diesel. So I designed this airplane for the Delta Hawk diesel for myself and my family, what we really wanted to do. And found that it was a big deal. So the Green Flag Challenge then came along, and our numbers said that we'd win it pretty much hands down if we could get it built in time. And the issue was, do we have the dollars to do that, and we have the resources?
What do you expect the weight to be at? What do you expect the weight?
What do I expect the weight to be at? We're targeting 1,250-pound empty weight. The aircraft is designed around a 3,100-pound gross weight.
Full-scale load testing?
Full-scale load testing, absolutely. One of these pictures has got 5 monkeys standing on our wing. Actually, it's not even our wing, it's our internal fuel tank core assembly. It's part of the wing.
What G loading?
That remains to be seen. My goal is 9G loading.
9G holes in it?
Yeah.
Are you using exotic composite?
Am I using exotic composite? No, not really. These are carbon fiber, Kevlar, and fiberglass. using Kevlar fiberglass up front for its robust durability and impact, and for its electrical transparency. Didn't want carbon fiber interfering with anything up front that they might be using with portable radios or electronics. But the wings are all carbon, and a lot of the foam materials are even off-the-shelf stuff. Spider foam, you know, fairly low-density spider foam. We do have some pretty exotic core materials. The yellow stuff that you'll see in some of the photos are core cell, and that's extremely expensive, but it's an underutilized core in aviation. I'd like to see it get out there a little bit more. Yes, young man. Am I selling plans for it? Are we going to get kits out there, and how much will they cost? The young man would probably like to know that when he's able to fly. He gets up there. I don't know. You know, the thing about this is that the cost of the airplane is very low from a material standpoint. It's very low from a labor standpoint. It should be possible for this to radically impact the cost of getting into an airplane of this caliber. But it ain't going to work out that way, folks. I'm sorry to let you know. You've got airplanes that cost $130,000 that it's competing with. And the value proposition will probably be that this kit is just as expensive, or maybe a little bit less expensive than everybody else's. And that has to pay for the extreme cost of getting there. There will be multi-million-dollar investments required to bring this to market at the volume that it's going to take. I told people a long time ago that from what we saw in private disclosure, we need to build 10,000 of these things yesterday. And that's going to take some real horsepower to invest in the necessary tooling to do that. So I see it being like a VCR it was back in the day. You know, I remember buying a 4-head VCR with $390. It was a big deal, you know. Nowadays, 15, 20 bucks, and you can buy a digital thing with one moving part. And so that's really where this will go over time. I think that the kit will become an affordable aircraft, and it will probably be in high demand as an expensive aircraft at first.
Could you give a little more detail on the placement of the holes in the 6 horsepower blower you spoke of? I
didn't speak of a 6 horsepower blower for Synergy. That's from Boschnitz's work. With respect to our boundary layer control system, the placement of the holes is behind the maximum thickness. So we're using the maximum thickness and the natural laminar flow of the body as an inertial separator. So the airflow coming over the top takes any dirt or foreign matter or water or ice and tends to separate it away from the actual surface, so we don't ingest nearly as much of the stuff that complicates boundary layer control by using it in the aft section. Yes?
There's no air that's blowing through those holes. It's a natural flow process.
The question is, there's no air that's blowing through the holes. It's just a natural process. No, I don't believe that blowing is the way to control the boundary layer. It can be done, but blowing was chosen as a method because we have bleed air from a compressor on a jet engine. What we really want aerodynamically is suction. We want to take the stagnant air and remove it, re-energize it, and spit it back out. So what we do with our control air is we take it from the aft section of the wing, we run it into the engine compartment, okay? It's run through the blower and over all the cooling components. Your oil cooler, your air cooler, your intercooler, your exhaust, your turbocharger, and by the time it's done that in the contracting volume and exits the vertical slot underneath the prop, it's an exhaust augmenting heated airstream that delivers significant cooling thrust.
It's like a number of angular connections in the airfoil. Aren't you getting interference directly?
Yes, angular connections of the airfoil, and the question is interference drag. That is really misleading to people, and I mentioned it earlier in connection with biplane interference. What causes an interference condition at an intersection has nothing to do with the intersection. There's nothing that the air says, oh, I can't handle a 90-degree corner that's, if I look at it from straight on. If it's a 90-degree corner, I can't handle that. What causes the interference is what's happening to the air over here, what's happening to the air over here, what's happening to the air over here. And if we have a big fight happening across the surface, then we'll get interference drag. So this is version 18, and the lens have changed completely. But when you look at it in 3D, you'll find out that there's a big stagger. Here's our quarter chord line, here's our quarter chord line, and so there's actually a lot of three-dimensional transition happening there. But what prevents any significant interference drag is the fact that this is a pressure surface, this is a pressure surface, and this is a pressure surface. I'm sorry, I did that wrong. The outside of the surfaces are all pressure surfaces. The inside surfaces are all suction surfaces. And so they're not having an argument across a surface about what the air is supposed to be doing. Now, when you get to the center section of the wing, and the wing to fuselage junction is always a problematic place for interference drag to occur. And it's hard to deal with. It was hard to deal with even on Synergy. On Synergy, we have it easy. The reason we have it easy is I don't have a big bump in my displacement volume on that graph where my wing starts. It comes to the wing, and as our sectional volume increases, it goes outward. So we actually are starting to pressurize the air out here about the time we're starting to need it to go back in here. That means that pressurized air out here is seeing suction air there, and we're causing the airflow to go back where it was before. Right? There's a lot of complicated stuff to that, but that's the simplest explanation I can give you about why we don't have any real significant interference drag issues to be concerned about on Synergy.
Are the passengers and fuel pretty much on the center of gravity, and how does that handle center of gravity shifts?
The question is, are the passengers and fuel on the center of gravity, and how do we handle our center of gravity shifts? Boy, that was one thing I didn't plan for it. I wish I could claim credit for it, but it just worked out beautifully. Solo, you're flying a lightweight ship and you're as far forward as possible. So you've got that's actually your most rearward CG configuration you can normally get. It makes for a super awesome handling. Obviously I haven't flown except in my mind and in the simulator, so to say that it's not proven. But as you add weight, you need the center of gravity to move forward on Synergy. Because we want to maintain the same proportion of downloading on the elevons with gross weight increase. So as the plane gets heavier, we want to push down a little more with our tail. And it turns out that there's no way you can load Synergy that doesn't do that and keep the CG just dead on. It actually has a more than a 1 foot range of CG, but you can't make it move that much. Yes?
I'd like to hear a little bit about how long you've been working on this project and the history. Just
a little more on the history and how long we've been working on it. Well, I think I've been working on this since 1977. I just didn't know it. I don't know how to describe that history except to say that it's always been on my mind how to get laminar flow, how to get wake propulsion right, how to get boundary layer control that works, how to get long wingspan performance in a short wingspan package, how to make it not ugly. I don't know. It suddenly came all together in one day. I was at the computer and I had just finished reading some paper, and suddenly eureka. One of these moments. I came running out of the room, screaming at the top of my lungs to my wife, "Holy cow! You're not going to believe this." So that's about all I can tell you about that. Now, since that moment when I lost my mind, I spent thousands of hours researching to find out how close anyone had ever come to doing it this way. I found out we've been really, really close many, many times. But even the people who advocated for those ideas and technologies didn't quite connect the dots, and they actually didn't necessarily believe what they were seeing.
John, how do you expect icing to impact the design?
How do I expect icing to be addressed or impacting the design? You know, icing is a significant issue for a certified airplane. I'm not really too concerned about it, but I've thought about it a lot. And I've designed ways that the structure is favorable to the routing of heated fluids, to using electrical de-ice. I think good natural laminar flow airplanes are inherently less ice susceptible than others. Our primary ice susceptibility has to do with our control surfaces and whether or not our tails are affected. This is a big problem, and so at the level that we're at right now, we've studied it on a preliminary basis, a conceptual basis, and I don't see any big red flags coming, but I'll be trying to work with people who are more expert in that field. One thing I will not be doing is putting anything on there like boots that would destroy laminar flow.
Will the full-size model have flaps? What about the tail volume coefficient?
Okay. Will the full-size model have flaps, and what is our tail volume coefficients like? Yes, the full-size model has a split flap from boom tube to boom tube. It's 8.5 feet long. It's there mostly as an air brake, so we have some way of adding to drag, but it does significantly increase our maximum lift coefficient. In order to demonstrate the CAFE minimum flat, 2.3 maximum lift coefficient must be achieved, which we can achieve through a combination of flap and suction. As respects to tail volume coefficients, even though this looks like a short couple, we've got about 24 feet of horizontal tail in terms of its width and 44 feet of area squared. So our tail volume coefficient is normal for an Elevon equipped airplane. Not Elevon, I meant oh my goodness. Full flying tail, what do we call it?
Empennage.
There we go. All right, and the same thing for the vertical tail volume coefficients. We have winglets and vertical tails. In fact, we have 4 of them that are high aspect ratio, and that they're actually already positively loaded. Those factors dramatically increase the stability in both the horizontal and vertical planes. So don't let the short coupling fool you, it's solid as a rock.
One question related to that when you have short and same level of force in quite wide area for the plane, and that means that we small get moment to the wide area and so on high downforce.
Yes, we're talking about. Yeah, we have a lot of drag because we have a lot of area because we have a high down force. Is that what you're saying?
Yes.
Yes.
High downforce is
High down force equals high wing rate. Yes, absolutely true. Except that we're not putting it where we normally do. If I have a conventional tail on this plane up here, it's nice when it's back a ways. I can make it smaller, and I can minimize the area, and I can minimize the downforce. That's the normal way to reduce the drag. But if I put a wing, not a wing, if I put a tail above and behind a wing tip in this location, now I want to throw as much air this way as I can, as hard as I can. There's an optimum. In the scientific literature, about 8% downforce delivers the optimum span efficiency for a continued wing configuration, like a C wing or a box plane. Okay? So if I've got an 8% download based on my gross weight, that mandates that I move it very far forward, or I have a plane that wants to do loops. So by moving it forward like this and delivering about 8% of gross weight in downforce, we're loading the tails a lot more than you normally would, and you'd think that that would be drag. But it's not. It's drag reduction. It's the same thing as having more wingspan and having better L over D. You added 20 feet of wingspan, but your L over D went to the moon. How did you do that? By adding wetted area and additional wing area. It's simple. You reduce the big penalty of the use drag. So a lot of counterintuitive stuff about that. One thing I forgot to mention in conjunction with this aspect of the double box tail is that because of it being short coupled, we have extreme control authority. But we have extreme control authority without a lot of travel. Okay? I was watching the videos in close-up and close-up telephoto views, and this is my control travels when we're flying that quarter scale model. Okay? That's the amount of control travel. And at first we had too much control travel. That was one of the reasons people criticized the landing. It was on the video. But the guy was holding it all together and he was just totally over controlling it. And I was telling him to land with a military style rollout and everything else. And the airplane doesn't need that much control authority. And the consequence of that, and another aspect, is that we don't see the likelihood of any stall spin behavior whatsoever with this plane. I've built quite a few models that will neither stall nor spin, and if that maintains its way into the full-scale article, I think we've really got something. What I see in the simulator is bobbing like in an arc. Just won't get there.
Why are you persuaded about it?
I'm sorry, I missed that.
What was your reason for shifting away from electric propulsion?
What was my reason for shifting away from electric propulsion at this time? I have a lot of intense work to do to make my full-scale electric motor concept work. And I was either going to have to immerse myself in that or immerse myself in the airframe. I thought the airframe was going to be easy and the motor was going to be hard. It looks like it's the other way around. It's on my mind all the time. I mentioned that amphibian. I think that the appeal of low and slow flight is strong for a lot of people, and it's very strong where we live. We have high mountain alpine lakes all around us, and nothing would be cooler than for us to just take off and fly up to a lake, land, and fly fish for a while and come back home. I think that's the coolest thing in the world. So I'm very motivated to get to the point where we have other iterations of effective, efficient, quiet, amphibian-capable flight. Yes, back there. It's on my mind all the time. I mentioned amphibian. I think that the appeal of low and slow flight is strong for a lot of people, and it's very strong where we live. We have high mountain alpine lakes all around us, and nothing would be cooler than for us to just take off and fly up to a lake and land and fly fish for a while and come back home. I think that's the coolest thing in the world. So I'm very motivated to get to the point where we have other iterations of effective, efficient, quiet, amphibian-capable flight. Yes, back there.
Hi, John. How you doing? My name is Ricardo Foster from the Virginia Beach area. I just wanted to thank you for what you're doing, and I have a quick question. Can you give us a take on your greatest challenge and a great success that you have had with this project? Thank you.
Oh, thank you very much. I really appreciate that. A take on my Green Flight Challenge. Is that what you're asking for?
Yeah, what are your greatest challenge with this project?
The greatest challenge? The greatest challenge here has been communication. Everything that you see, every single thing that you've heard and that you see, I've been saying for a long time to people in private, and they don't get it. And so when you have a situation where you need to raise capital to do things the right way, there's this credibility gap. Like, who am I? Well, guess what? I'm nobody. Okay? We just have to do our work and somehow manage to feed our faces while we do that. That's all it's ever been about. And we've managed through the same attitude that most of you guys have and that this organization displays. We've managed to do that, and we will just keep on managing to do that until we're done.
And a great success, please.
Thank you.
you mentioned high speed and the Delta Hawk. What do you think the cruise speeds will be? Horsepower variant?
I'm not going to talk about performance specifications at this point. First of all, you guys wouldn't believe me. And second of all, we don't know. We haven't seen that actually demonstrated yet, so it's a little bit silly to talk about. As far as the specifications are concerned, I wanted a big engine in this thing. And the biggest engine that Delta Hawk offered was 200 horsepower. So I designed the airplane for that. Now, at this point, we can't get a 200 horsepower Delta Hawk. We can get a 180, but that's fine. That's perfect for the Green Flight Challenge, as a matter of fact. Yes. Do we have a Delta Hawk engine? No. That's one of the biggest factors to whether or not we're going to make it in time. No, only in general terms. Yeah, only in general terms. Because it's a liquid-cooled engine, and we've got a really beautiful opportunity in terms of radiator space and the design of the cooling compartment. It doesn't look like there's any challenge there, but man, I've got contingency after contingency after contingency built in so that we can open it up and get more cooling if we need it. Yeah.
It seems like you spent a lot of time on molding and elaborate manufacturing processes. With all the unique aerodynamic things that you're doing, I'm wondering why you didn't go in a more one-off, rapid prototyping direction first.
Okay, guilty as charged. The question has to do with why did I invest so much time in modeling and high-level design integration instead of just getting something flying and prove things out and so on. And the answer is I can't do it that way. I'm an all-or-nothing kind of guy, and to me this kind of breakthrough deserves to be shepherded all the way through, start to finish. Nothing would kill all of these technologies deader than a doornail faster than to bring them into committee within the typical structure that we have for aeronautical development. I can't tell you how many times I've sat down with PhDs, in some cases PhDs who taught me some of this stuff, and had them talk the entire program out of existence in the span of 15 minutes. So it just has to be done. It has to be done right.
So the fear is without production tooling, that when the finished aircraft is a success, production tooling is necessary, the money that's necessary will necessitate your tooling to survive.
Well, I'm not sure if I'm following the argument there. Well, production tooling doesn't exist. This is being built with a one-off. If we were funded according to the original plan, we'd be building production tooling. But this is a one-off. And I'm exploring ways that are not tooling dependent. So there's a lot of stuff that looks complicated that isn't. And I want to speak to that integration and design thing for just a second, because if you take if you take a month to make something in SolidWorks, combine the attributes of 17 parts, you saved huge amounts of assembly and complexity down the road. I mean, you didn't need that jig, you didn't need this part, you didn't need that weight, you didn't need this liability. It's all built in. And so the way that the kit is envisioned is that everything that has a complex geometrical shape is built in a factory. And if it's built in a factory, it's got all this stuff in it. So my wingtip right here might have, it's got a complex geometrical shape, so it'll show up to the home builder as a finished product, but it's going to have the fuel cap door fully integrated. Okay, it's going to have the chase for the wiring. It's going to have the wiring and the lighting and the antenna stuff built into it. So everything that's downstream complexity is built into the complex parts. I didn't hear that.
Integral versus bladder tank fuel cell.
Integral versus bladder tank or fuel cell. Integral is fine for this type of construction. It shouldn't be any problem at all. We have a capacity for a ridiculous amount of gas. If you're flying with Jet A and the Delta Hawk diesel in Synergy, you have a transcontinental, trans-Pacific airplane. You can go anywhere you want to go.
Controls. One of the things I think is pretty cool about the cockpit design is it's a little kid in a candy store for me, because I always wanted to be the guy in the F-16 on the pointy end of the airplane, right? So the cockpit experience up front is you're solo, you're surrounded by all the stuff you want. It's not in your way, you've got a beautiful unobstructed view. But right behind you is a standard side-by-side dual arrangement. So you can fly it solo, you can fly it tandem dual, you can fly it side-by-side dual, or you can be an instructor with 2 students. Or you can fly side-by-side sitting with your wife, and you can put your VIP 12-year-old in the front seat. How about that?
Where do you ingest the cooling air?
Where do I ingest the cooling air? Under the wing inlets. I'm sorry, under the wing root fillet. We kind of mock that up. That's not how it actually will be. In fact, they're way up. We're using mostly wet layup, but I've got some infusion parts for vacuum assisted resin transfer. I'm not using any Thank you all for your questions. It's been a real pleasure. We're going to take this party to the Aero Innovate thing, which is in the Innovation Center. That's where we're kind of be hanging out for most of the day today. And then we'll be around there from time to time if you have any questions. Thank you very much.